Hello, YouTube. We're doing power functions today, so let's see about that. All right. What's a power function? You were saying? X raised to a power, right? So x squared, x cubed, x to the fourth, x to the fifth, right? Okay. So, what's different about x squared and x cubed? Now, these are mother functions. Can you picture them in your head? X squared and x cubed? Let's see. Let's find out. All right. Curvy. Well, they're both curvy. All right. So y equals. Hello. Wake up. Okay. So y equals x squared. Whoops. Squared. Looks like this. Zoom 4. We call that an even function. What does that mean?
Domains are equal.
No, not the domains. Yeah.
Is it the axis symmetry is the y-axis?
The y-axis is the axis of symmetry, right? Okay. So, is it true that f of -1 is the same as f of +1? Yeah. All right. So if f of x is x squared, f of -x equals f of +x, right? -1 squared is 1, +1 squared is 1. -2 squared is 4, +2 squared is 4. That's an even function. It has y-axis symmetry. It's also called an even function because the exponent is even. So what about x to the fourth? What's the difference? Is there a difference? Does it have the same characteristics though? Hello, move. Why is this not moving? There you go. X to the fourth, regraph. I didn't change it. X to the fourth. Why is this getting stuck like this? 4. There you go. Go. All right. How's that different? Well, is it still even? Still even, but it still goes, well, all right, you tell me, what's the domain? What x values can you plug in? All real numbers. What's the range? Wait, there's a coffee clutch over here. I don't want to interrupt. You ready? You done? You finished? You sure? What's the range? Greater than or equal to 0. All right, so the domain is all real numbers. Give me a pen. From -infinity to +infinity. And the range is greater than, why is this lagging today? Yeah, same thing, yep. Greater than or equal to 0, you can plug in 0 and you get 0, right? Okay, but let me ask you this weird question. What's the limit as x approaches infinity of this f of x? As x goes to +infinity, what's y doing? Look at the graph. As x goes to +infinity, what's y doing? Also going to +infinity. We have to start talking about this thing called the limit. The basis of everything in calculus is what is a limit. And the limits come from the discussion of domain and range. The limit actually describes the shape of the curve. What if I said, what's the limit as x approaches -infinity for this function? As x goes to -infinity, what's y doing? Going to +infinity. Okay. But you knew that because the range includes +infinity. Yeah. Yeah, what is that? Number pile? What? There's a website, there's a YouTube channel called Number File, I think. And they're out there saying this crazy stuff like, what are they saying? Wake up. No? Should we not? Why is this acting stupid? Okay. Something is lagging my computer here. As x goes to +infinity, y goes to +infinity. As x goes to -infinity, y goes to +infinity. These are positive, that's negative. That's a positive. Those are x's. That's f of x. Those are x's. Those are all x's, yeah. Huh? The y is the f of x. No, it didn't. As x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches positive infinity. I'm getting some weird lag here on my... I can't get a new page. What the heck's going on? Oh, God. How do I get a new page? I can't get a new page on here. Oh, well. This is not good. Okay, I have to restart my smartboard. Yeah, I guess we can't do math today. Oh, well. Yeah, that's the problem. I'm trying to record this from scratch. We don't have screencasts for this. Because we don't. All right, anyway, let me just do a little attendance thingy. Brandon, Shanice, Savannah, Jalen, Pascal, Aaron, Rachel, Catherine, Jaron, and Emily. And we got Cheyenne, Danielle, and Sarah, and Jared, and Charlotte, and Christine, and Ronnie, and Kevin. Oh, we're missing Rebecca, right? Liz, and Neela, Eduardo. Okay, settle down. Here we go. Hang on. We're missing here. Kester. Okay. All right. So, all right, listen. All right. So, if f of x is x squared, f of negative x equals f of positive x, right? Negative 2 squared is 4, positive 2 squared is 4. Negative 3 squared is 9, positive 3 squared is 9, right? Same thing happens if you have a 4th power, 6th power, or 8th power, okay? Negative 1 to the 4th is what? 1. Positive 1 to the 4th is 1. Negative 2 to the 4th? 16. Positive 2 to the 4th? 16. These are called even functions. They have y-axis symmetry. Okay. Then what else do we want to say? Let's see. Is this graph still on? That's it right there. What was the domain? X is all real numbers. Negative infinity, positive infinity. Okay. And y is? What are the what's the range? Greater than or equal to 0. Okay, good. Now, what about the limits? That's what I wanted to talk about. Okay. What's the limit as x goes to positive infinity of f of x, which is x to the 4th? Positive infinity, right? As x goes to positive infinity, y is going to positive infinity. Okay. What's the limit as x goes to negative infinity of the same function? It's also positive infinity. As x goes to negative infinity, y goes to positive infinity. Okay, yeah. Yeah, plugging in bigger and bigger numbers to see what happens, right? Now, we don't always talk about limits at infinity. Sometimes we talk about limits at a point, at x equals 2 or something. We'll get to that. We've got to start talking about limits. We're just trying to get used to the idea. All right. What about odd functions? You screwed? That's it? Okay, what if it's x cubed? We're back to that? All right. Now, that doesn't have y-axis symmetry, does it? We don't call that an even function. We call that an odd function because it has what symmetry? Not x-axis symmetry. X-axis symmetry means it would be reflecting across the x-axis down here. Not x-axis symmetry. Thank you. Not y-axis symmetry. We said it's not even. Y equals x symmetry. Yeah, okay. In this case, that's true. I'm going to say origin symmetry. If you take any point, let's say 1, 1, right? Plug in 1, cube it, you get 1, right? And you reflect it through the origin, 0, 0, the same direction, same distance, you end up on the curve again at the point negative 1, 1. Okay, so let's talk about that. So what if f of x is an odd function? X cubed, x to the fifth, x to the seventh, x to the ninth, okay? F of negative x is negative f of x. If I plug in -1, what do you get when you cube it? -1. So f of -1 is -1, which is the opposite of f of 1. What's f of 1? Plug in 1, you get 1. F of -1 is -1, f of positive 1 is 1, -1 is the opposite of 1. That's called origin symmetry. Let's try it again. What if I plug in -2? You got it? It's yours? Okay. Go ahead. You can get it. Go ahead. So what if I plug in 2 and -2? What's -2 cubed? -8. What's positive 2 cubed? 8. Is it true that -8 is the opposite of positive 8?
Yes.
Yeah. So if I plug in 2, I get 8. Reflected through the origin, I ended up at the point -2, -8. -2, -8. Thank you. Okay? That's origin symmetry. What's the domain now? What x values are you allowed to plug in? More than that. More x values. Right. So in other words, all real numbers again. Okay. So x is between -infinity and positive infinity. I don't know where this lag is coming from. All right. And what about the y values? Look at the y values. Everything also. So between all real numbers, -infinity and positive infinity. So now let's say, what's the limit as x approaches positive infinity for this f of x? As x goes to positive infinity, y is going to positive infinity. And what's the limit as x approaches negative infinity for this function? As x approaches negative infinity, y is going to negative infinity. All right, so just starting to talk about limits. That's all we're doing, talking about limits. Now, this is true for any odd function. Did I write odd somewhere? Where's it stuck? There it is. This is true for every odd function. I say this is an odd function. Okay? If I could say all the same stuff about x to the fifth, x to the seventh, x to the ninth, x to the 11th, and so forth, right? Anyone got a problem with any of that? Okay. So now, let's go straight to the homework page. What's the homework? Page 196, multiples of 10. Take a look at number 1. Number 1 says, can you graph y equals x plus 1 to the fourth? Huh? When is the test on this stuff? Well, if you take a look at Edmodo, got it in here somewhere. There it is. Chapter 3, assignment sheet. Let's take a look at it. All right. This was last night's homework. This is tonight's homework. This is tomorrow. This is Thursday. This is Friday. Take a look at next week. Test is next Friday. Okay? Test next Friday, pre-test next Thursday, right? All right. So we're going to be talking about rational functions next week. Rational functions next week. Yesterday was quadratics. Today's power functions. Tomorrow's polynomials. All right? That's all. That's what we're doing. All right. So here we go. So what if I want to graph? All right. Let's say I want to graph. Let's see. All right. So this is page 196, number 1. How do you graph y equals, or f of x equals, I should say, x plus 1 to the fourth? Now think of it. Is that what's the mother function? What's that based on? X to the fourth. Now x to the fourth, what do you know about x to the fourth? Is that an even or odd function? Even. So it has y-axis symmetry or origin symmetry? Y-axis symmetry. So the domain is x is over numbers, y, the range is Greater than or equal to 0, right. Okay, so you know what x to the fourth looks like. It's a lot like x squared, except we saw it, a little flat on the bottom, right? A little flat on the bottom. But it goes to the same limit, same domain, same range. Okay. So how do you graph x plus 1 to the fourth if you know what x to the fourth looks like? Not down 1, not up 1. To the left one, to the left one. Okay. So so let's just confirm that on Ziggy. Okay, Ziggy, where are you? All right, let's make this x to the fourth. There's x to the fourth. Now you said x plus 1 to the fourth is just that same exact graph shifted 1 unit to the left, right? Let's confirm that. So quantity x plus 1 to the fourth. Why does it do that? It got stuck. Keyboard, dumb keyboard. And you're correct. All right, so what do you do if this was a test paper or your homework? You draw both of those curves. One is based on the other one. That's the work, in other words. The work is, you know what x to the fourth looks like, just shift it. Okay? All right, that was easy. What about number 9? Okay? Number 9 says graph x minus 1 to the fifth plus 2. Okay. All right, so let's do number 9 from the homework page. So number 9, here we go. Give me a pen. Give me a blue pen. I like blue. Okay, number 9. What does y equal to x minus 1 to the fifth? What does it plus 2 look like? All right, so who's the mother function? X to the fifth. Is that even or odd? Odd. So it has y-axis symmetry? No, origin symmetry, right. Okay, so it looks sort of like x cubed, sort of? Okay. What does the negative one do? Shift 1 to the right, horizontal translation to the right. And what does the plus 2 do? Move the whole thing. We're adding 2 to all the y values, shifting up to a vertical translation 2 unit. All right, so let's see if that's true. Let's take a look at that. All right, I'm going to clear that. And let's say what x to the fifth looks like. Let's see if we're right. X to the fifth is a lot like x cubed, isn't it? Look at it. F of 1 is 1, f of negative 1 is negative 1, just like x cubed, right? It's got origin symmetry. It's an odd function. The domain is all real numbers. The range is all real numbers, just like x cubed, right? Very like x cubed. Okay. The limit as x goes to positive infinity is positive infinity. The limit as x approaches negative infinity is negative infinity. Perfect. Okay. So now you said if I do the minus 1, what happens? Goes to the right one. All right, let's see that. Okay, so x minus 1 to the fifth. Let's see what that looks like. Shifted 1 to the right. Perfect. And what does the plus 2 do? Up to, yeah. That's really the steps, yeah. Show what x to the fifth looks like. Based on that, show what x minus 1 to the fifth looks like. Based on that, show what x minus 1 to the fifth minus plus 2 looks like. All right, so, I don't even have to write it that way. Look, let's do it this way. y1 of x minus 1. It's a composition, isn't it? Here's x to the fifth. Here's x minus 1 to the fifth. Same answer, yes? All right. And then I could then write y1 of x minus 1 plus 2. And it takes the last curve, shift it up 2, instead of going through 1, 0 goes through 1, 2. Okay? So let's see, let's make this stand out. If the original curve, let's say, is dotted, and the final answer is thick, let's see what it looks like. So here's x to the fifth, dotted. Here's x minus 1 to the fifth, solid. And here's x minus 1 to the fifth plus 2, thick. Ta-da! Okay. There you go. And you could do 3 different if you want, yeah. I usually put it on one graph, but you don't have to. Yeah. If it makes it easier, yeah, sure. That's fine. All righty. So you do 17. Go ahead. Boards, groups, go. Need a marker, need an eraser, need a board. Number 17, take out your book. Page 196, number 17, let's see it. Let's see what you got. This is a nonlinear regression using power functions. All right. Number 17, CBL. What the heck is a CBL experiment? All right, listen up. All right. Every group gets a board somewhere in the middle of your team, please, so you can all participate. All right, you can use the big boards in front instead if you want. All right. Take a look at number 17. Where's your textbooks? Not even textbook, just one. Just one. No? You got a book? You got a book? All right, good. You got a 0 today. Book? 0 today. Good. I can too. Watch me. Book, good. Book, good. All right. Jeez. Well, then you should have told me about that. Yeah, a little late. All right. So, listen. It says this is a CBL experiment. What is that? What does CBL mean? You know? Have you encountered that before? Do they do that in science class anymore? They used to. There's these monitors, these probes that you can attach to your TI-83 or 84 that can measure, that can measure changes in light intensity, changes in temperature, changes in humidity, changes in, different motion detector, right? You can attach these little probes to your calculator and then take measurements over time and graph it. All right, and that's what they did. Here we go, CBL experiment. All right, Dave is conducting an experiment to estimate the acceleration of an object due to gravity. In other words, G, right? What's G? Okay, but I think we're in feet per second here. 32, should be about 32 feet per second, all right? Let's see if we can get that, all right? Okay, David takes a ball and drops it from different heights and records the time it takes for the ball to hit the ground. Using an optical laser connected to a stopwatch in order to determine the time, he collects the following data, which you could do with a CBL connected to your calculator. All right, so enter the data. Go ahead. How do you do regression? Second, stat plot on, make sure it's on, right? Otherwise the Zoom 9 stuff doesn't work, right? Okay, then what? Stat, edit. Okay, you guys got a textbook too now? Amazing. Where did they materialize from? All right, so enter the data. Go ahead, you do it. Use a calculator, a real one in your hand, if you got one, or on the screen. Go. All right, what's the data say? 1.03 seconds for 16 feet. Dang it. There you go. All right, 30 feet took 1.365 seconds. No. This thing's getting all laggy. I don't know why. Where am I? 1.769 seconds it took to fall 50 feet. Okay. 2.093 seconds it took to fall 70 feet. And 2.238 seconds it took to fall 80 feet. So let's fill in the feet. So your domain is time in seconds. Your range is height in feet, height fall distance, right? And what was it? It's 16, 30, 50, 70, 80. Okay, 16, 30, 50, 70, 80. 50, 70, 80. All right, so if you don't have a book, that's really all you need. All right, so part A. Draw the scatter diagram. Go. How do you do it? Well, on calculator. Zoom 9, that's all. So Zoom 9 it. As long as your stat plot is on. Zoom, 9 it. Okay. Well, what's that other stuff? No, I didn't calculate it yet. That's from the previous problem. Get rid of the y equals stuff. Hello? Okay, get rid of this stuff. This is the last problem. Get rid of this. Just that. Okay. Alrighty. Part B. Find the power function of best fit. Okay, go ahead. Find the power function of best fit. You don't have to write anything yet. Power function. Read the question. Wow, the Wi-Fi in this school sucks. Okay. I can't get my tablet to connect. You want a Wi-Fi hotspot, do you? No? All right, so this is what, 17? All right, so the first thing you have to write down is your y equals. Y equals what? Well, did you get it? What do I type? What should I do? What did you do? Stat, calc. Where's power? That's linear. First degree, second degree, third degree. Well, maybe. Fourth degree, first degree, logarithmic, exponential, power. Remember, exponential means something to the x, like 2 to the x. Power means x to the something, like x squared, okay? So that's one we want? Yeah. Okay, enter. And what else do I usually put here? L1, so second one, comma L2, comma Y1, so we can store it somewhere. Vars, Y vars, function 1. Enter. And what I forget again, I always do. On purpose, it's a teachable moment. So what do? Diagnostics done. So second catalog, D, to see how good the fit is, right? And diagnostics on, that's part of the answer for part B. You have to write that down. All right, so second enter, so I don't have to type a lot. I typed a lot anyway. And there you go. So what do you write down on your answer page? On your homework, let's say. Y is approximately what? 7.3? Okay, so 15.973 times x to the 2.002-ish? 2.002-ish. And what's your r squared? It's about, that's a percent? 99.996? 99.996. That's about as good as it gets, unless they give you bogus data. They do that. Okay, so that's part A. No, part A was a scatter plot. Part B. Now, what's part C? Part B for 17 says, part C, graph the function you found in part B of the scatter diagram, see how good it is. Predict how long it'll take to fall 100 feet. Okay. All right, so graph it. We already have it in y equals, right? Just graph it. So how good a match is it? Pretty darn good. Look at it. Very accurate. So it looks, if they didn't tell you to use a power function, would you have used maybe a linear function? You could have, but this is better. You're not going to get a linear function that's going to get that big in r squared, right? You want a linear, a line of best fit, you could do that, but it's not going to be a great, accurate result. All right, so that's A was the scatter plot, B was the equation, C was the graph. Now D, how long does it take to fall 100 feet? Now what are we doing? Look at the data. Stat, edit. What are we doing? If we're looking for when we fall 100 feet, are we interpolating or extrapolating? Extrapolating. We're extending the domain, right, and the range. In this case, are we extending the domain or the range? Which one? The 100 goes where? Domain or range? 100 feet. Range. This is how, right? L2, the y values are how far you're falling, right? So how do I find out how long it takes to fall 100 feet? I can't plug in 100 because what you're plugging in is time. This is a function of t. So look at the graph and see when it hits 100. Okay, so y equals 100. Move. And see what they expect. The y values, when they're 100, what's the x value? The t is the x value. No. Huh? Well, how are you going to solve it, though? Or the solve key? You could do that. I don't usually do it that way. Now, look at this. The window's no good if you don't see the y equals 100. Why? Because you don't know what the window is. The window, y max, is not 100. So, what are you going to do? Make it so. If I'm going to be here anyway, I might as well. I'd like to see the axes, so I'm going to make an x min of 0 while I'm at it, and a y min of 0 while I'm at it. I don't have to, but this has to be more than 100. What do you want to be? 100 would be hard to see. More than 200? Okay, 200. And then the scale for x being 1 is fine because you're going from 0 to 2 seconds. Wow, big deal. But the y scale, is that good to go up to 200? What does the y scale mean? The tick marks every one. What? 200 tick marks? You're not going to see it. So what do you want for your scale? 100. What the hell? All right, graph. So there's the scatter plot, and there's the curve, and there's y equals 100. Oh, dang it! I still don't like it. Why? The y max wasn't big enough. Now the x max isn't big enough. All right, so change it. Well, the 500 seconds, really? It only goes up to 2 seconds. How about 10 seconds? Yeah, that's even better. All right, so how do I answer part D? How long it takes to fall 100 feet? Super trace, intersect, bing, bing, bing. And you get 2.5 seconds roughly. Yes, okay. So, where did my marker go? I lost my marker. Dang it. All right, so did you get that on your own? Yeah. You did? Okay. All right. So, if, give me a pen, if y of t is 100 feet, then t is about 2.5 seconds. Even if you round off to 3 places, right? Whatever. Okay, so that's part D. What else? What's next?
Part E.
All right, what do they want you to do in part E? Part E says that this should be 1/2 gt squared. We got 15.973, was it? Wait. Yeah. 15.973 t to the 2.002. That's what we got for the displacement of this baseball, right? S is displacement in feet, t is time in seconds. Okay. But it's supposed to be 1/2 gt squared according to physics class, right? So is there a way you can estimate g? That's the question. But you would be wrong, because we're not doing meters and seconds here. No, we're in feet and seconds. It should be somewhere around 32 feet per second. But what are we getting here experimentally? We're not doing a theoretical approach. We're doing an empirical approach. What's the difference? We're using real-world data, but there's going to be some kind of error, right? It's not going to be exactly 32. But how do you get it? How do I get G? Solve for G. Now remember, it's an estimate. This says t squared. This should say t squared. There's a little bit of round-off error. So pretend that the t squareds cancel. How do you get G? Multiply that 15.973 by 2, right? Okay. So 15.973 times 2. So G is about 31.946 units feet per second. Right. Don't say seconds squared. It's not an area. Okay. All right. Any questions on 17? Because it's not an area. When you take a unit squared, the implication is that it's an area. If you take a unit cubed, the implication is that it's a volume. This is a rate of change. Okay? What we're talking about is the acceleration due to gravity. What is acceleration? How fast the velocity is changing. How do you measure velocity? Feet per second. How do you measure acceleration? Feet per second per second. How many feet per second your velocity changes each second? Right? Why is velocity feet per second? Because you're measuring your displacement over time. How fast your feet are changing every second, right? But that's not what I'm asking here. I'm asking how many feet per second you're gaining or losing every second. It's the rate of change over the rate of change, the rate of change of the velocity. Okay? All right. What's next? What's next? Okay, number 20, go. Go ahead, 20. Now that everybody's got books. Okay. Go ahead, 20. Another CBL experiment. Kathy is conducting an experiment to measure the relation between a light bulb's intensity and the distance from the light source. She measures a 100-watt light bulb intensity 1 meter from the bulb at 0.1 meter intervals up to 2 meters. Okay. And obtains the data to the right. Using a graphing utility, the T83 or 84, draw the scatter diagram with the distance as the independent variable. In other words, distance is the y value. And, sorry, I said it wrong. The distance as the independent variable, that's like the x value, and the intensity as the dependent variable, that's like the y value. Okay, go. And find the power function of best fit. Excuse me. Shh. Enter data. Go. How do you clear data? Go to the top, clear enter, right? Go to the top, clear enter. All right, so what do we got here? All right, so 1.0, enter. 1.1, enter. 1.2, enter. 1.3, enter. 1.4, enter. 1.5, enter. This is what, feet? No, meters. Okay. 1.6, 1.7, 1.8 meters, 1.9 meters, 2 meters. Alrighty. All right, then you have 0.29645. Holy cow, really? 0.29645. Okay. 0.26215. 0.20547. By the way, what units are these? The X's are in meters, but the Y's? What are the units of light intensity? Watts? It could be watts. It's probably lumens. Candles are lumens, right? What's a lumen? Is that one candle? All right, finish that off for the homework. By the way, that's your homework. Multiples of 10. All right.
Can I get you to write sometimes she doesn't believe I have extra help.
I have to write a note for this?
Yeah.
Are you serious?